let us find now the potential in the space charge region is a function of the distance from the metallurgical junction. Electric potential is a function of x. So this is what we said is like x on this side, like that is plus and that is minus. So let us we call this is xp and this is hn, right? So that was p and that was n region. Let us talk about the p region, right? The p region, and the p region means that it is from minus p to 0. X varies from minus xp to 0. Right? We define the electric field is minus d by p over the gradient of potential, right? The gradient of potential on the p side is equal to the electric field. This we have the electric field and the previous equation, right? We derived relationship for the electric field. So here the potential at this, we integrate the equation, and that can be written as minus, and to take the potential from the electric field from the previous equation, x plus xp into dx, right? I separate the variables d phi equal to e dx and put the value of e here, which we got yesterday.
Yes.
So that is equal to e and a by epsilon s, right? And x squared divided by 2 plus x and 2 xp plus some constant of integration, which I call is c, right? Okay, so let me potential is, the potential difference is important than the potential itself. So let us take potential here, A is 0. Field laser does it, the field, right? The field direction is this. So let the potential at this point is equal to 0. Let, right? Phi p is equal to 0 and x is equal to minus xp, right? So when we do this from here, we get c1 equal to e and a by epsilon s and xp squared divided by 2, right? We write x is equal to x minus xp, right? We write x is equal to minus xp, and then put it here, and we get the value of, because this side will be equal to 0, right? So we get the value of 0. सही रखना ना?
Sir. Yes, sir.
So now 3 into 2, right? Nothing सही है? तो मुश्किल को नहीं कर देंगे
No.
Simple. Phi of P equal to E and A by E S and x squared divided by 2 plus xp plus C1, right? And what is the value of C1? E and A. So that's xp squared divided by 2. So from here, when we simplify this, doing the necessary algebra, we get E and A divided by 2 epsilon s x plus xp whole square. So the potential at the P side values is this current distribution. Now the potential it
So the equation 4 it has z with a 2z. Side है sir.
In the end region, right? In the end region for x greater than 0, x n. So we get from here we have this equation, right? Then from here we get phi n. Phi p positive phi n now, right? Phi n will be equal to e dx.
Yes, sir.
Okay, e value will be n because of the region.
Yes.
We found the electric field yesterday in 2 regions,
Yes, sir. Yes, sir.
right?
Yes,
So you can find this is EP, you can write. And here you will write the EN. So phi n as a function of x will be equal to E and D divided by ES and xn minus xn to dx. This is equal to E and D by ES and x into xn minus x squared divided by 2 plus some constant C2. Now we want to find the constant C2. Right? उस bulk condition, boundary condition of Yoda boundary condition. This was boundary condition. Now the boundary condition, right? 8x is equal to 0. Both this is x equal to 0. The potential at the P region and the potential at the N region will join.
sir.
the two potentials will
Will
join together. It means at this, the two potentials will have the same value.
Yes, sir. Yes, sir.
At x is equal to 0, phi p will be equal to phi m. So you know?
Yes, sir.
So from here, question 4, right? And 10, sorry, 5. 4 and 5. You put x is equal to 0 there. X is equal to 0 here, and x is equal to 0 here. Right? And make them equal. This equation is equal to this equation, and put x is equal to 0. So we get here C2 equal to E and A divided by 2 epsilon s and to xp squared. So equation 5 can be written as 5 is equal to E and D by 2s. Sorry, by s. But it's not s. I believe s is over there. That's right. Okay. S are one diagonal or s there. Okay. And x n minus x squared over 2 and plus c2. So C2 is E N A over 2 epsilon s and 2 xp squared. Right? Okay. That is the potential of atom. This is the potential in the N region. Right?
Yes, sir.
So that's the data of the N. That's the junction dust. The space charge region or that's the positive there or the potential of the region of one की दस बराबर है. Potential increases against the electric field. सही था? Electric field stay away against potential the key increase key. So that to positive charge तरफ तो से potential increase key. Right?
Yes, sir.
So it starts from 0 because we say lit at x is equal to xp, that is equal to, right? So the total potential from here to here is called VBI. The potential difference, so
VBI.
So the VBI will be equal to this plus
This. Yes, sir.
सही है बोला?
Yes, sir.
So the VBI is equal to phi p plus phi n, right? And from there we find x e or 2 epsilon s n d x n squared plus n a x e squared. That is the built-in potential. It's a function of the doping,
Yes. After etc.
and it is the function of the region the width of the n side, no, not the n side, the space charge region of the n side. You know, this is xn is this, and xp is
This.
n side is this whole, right?
Yes.
So it would be like this. Look, it would be something like this. Starts from 0, right? And following this, it's kind of a square relationship, right? Yeah, it would be like something like this. Or we are just so this potential from here to here is V dr. And at this point, x is equal to 0, the two potentials will be the same. Right? Because there is application. When you plot this equation here, this is minus xp, and this is 0. When you plot this equation here, you will get some line like this. Right? Where? They know to be a so it will move something like this. So the two will then will have the potential from here to here will be constant. Will it be constant?
التصرف الخدشات مش تزيد.
شارد نشتا of درجة دي في زيرو ده
زيرو
زيرو شرط في potential زيرو
زيرو.
constant probably.
Yes, very.
Right? Okay. Okay. What is the width of the depletion region? Right?
Yes, sir.
The width of the depletion region. Depletion or depletion term का word space charges depletion region width. That right? This is the W word.
Yes, sir.
Right? So W is equal to xn plus
XP.
xp, right?
Yes, sir.
Now we can get this from the built-in formula, a full equation from 7, right? Here, 2ES 7 implies 2 ASBBI, right? Divided by E is equal to MDXN square plus NA XP square. That is enough.
Yes, sir.
तो दोस्त होगा xn और xp value का देना होगा सो तरीका,
Yes, sir.
right? We will have to find xn value and xp value. So let us eliminate xp from here. Suppose eliminate xp from here, right? So eliminate. So we use this equation. X n and d, the yesterday equation is equal to xp and a. So xp was super over c. X the x n x n x n and d is equal to, so xp eliminate xp. So that would be x n and D divided by NA. This is a question number 2, 3. So put 3N, right? 2. Two ES will be I divided by E is equal to ND xn squared plus NA, right? And D xn squared by NA, the whole square.
Yes, sir.
The scan resistance is NG NA plus ND square divided by NA and 2 xn square. R xn square is xn square from here will be equal to 2 epsilon SBBI divided by E and 2 and A over N A and D plus N D square. Our JXN mengubah para bersih. This whole thing to the power 1/2 bersih. Right?
Yes, sir.
Not from the same equation. If you want to put up what's the extend motor by this is in a vacuum, if we take xn from that will be equal to ND by that is not xn is equal to NA
XP divided by A.
XP, right? Divided by N D, right? That is 5. Mudabat that you all ago. 5 in 4. R eliminate. X A from 2. What's that sort of thing? X N eliminate. Right? So you get the value of XP. XP was assigned to ASBBI divided by E Semiconductor. And D over N A N D plus N A square. Our whole 1 over 2. Right? Я вам сразу 1 over 2 to zbrotny stopata wychodzi. A ta się square, eh? We don't need this.
Yes.
Right?
Yes, sir.
So 5 and this is the question number 6. So 5 and 6 in equation number 2. One. Huh?
Yes, sir, 1.
W.
Right?
Yes.
So W equal to will be I over E to power over 2 and and A by N G over 2 1 over N A plus N D to power 1 over 2 plus N D over N A to power 1 over 2 of this is 1 over N A plus N D to the power 1 over 2 take this common. So this equals this thing. And take this common. 1 over N A plus N D. And then here we are left with this and that is equal to N A plus N D divided by N A power N D. No skill. Now, this is square root here. That's good. This will be square rooted with this. So that will be 2 epsilon s VBI or E square root and that was to using moment the half. And A plus N G or N A and D. That is the question number 7. That is the weight of the
Depletion.
depletion region. So the weight of the depletion region depends upon again the doping in this formula. according to this formula. In A plus ND divided
And
and ANT, right? And VDR. Square root function of the built-in potential. A is the square root. In the numerator, it is the sum of the two, and in the denominator, it is a product of a very complicated relationship. Let me know when you finish this thing. So reverse bias, BIASED, bias junction. Right? And now we bias the junction. We apply a potential drift. And such that the polarity is reverse biasing. Before this, up till now, we were doing only simple p-n junction without any external potential difference applied to it. Now we want to see what is the situation of the width of the space charge region if we apply a potential which is usually referred to as reverse biasing. And reverse biasing, right? And it's to the N side you apply a positive, and to the P side you apply a negative. And it's called reverse biasing of the p-n junction. Did you know? Right? That is a p-n junction. Right? Well, that is supposed to metallurgical junction X equal to 0 out of the cover. That is N, that is P. This will get negative, this is positive, right? Now, the electric field is in this direction. Inside the junction, the electric field is in this direction. For the N or for the P region, which direction there is the electric field? Delta or delta? Delta that direction should turn. Delta? Turn away. The light is fine. Delta nicht of field. Now we want to bias it. That is the metallurgical junction. This was X N and this was minus XP. Now when you apply this with a positive on this side with a negative. That's it. Right? That's P side, you apply this with. No. This is the electric field here because of the external electric field is in this direction, right? Or the internal electric field is also in this direction. The two electric field will enforce each other.
Yes, sir.
And the potential difference should increase because the two fields are in the same direction, equal direction, correct?
Okay.
They equal direction, then, right? So we think that the depletion region width should increase because of the potential, because of the two electric fields and potentially raising of the potential. We will suppose that, right? Let us see, right? So now we will think that it is more difficult for an electron to cross the barrier
Yes, sir.
because the opposite electric field is higher,
Yes, sir.
because the potential is now more.
Yes, sir.
And if we write this in the energy band diagram, if we write this in the energy band diagram, that is E, right? So it will be something, if that is the Fermi energy, now because of the potential difference, the Fermi energy will get lower. You know, in the initial, when there was no biasing, it is now not in equilibrium, right? Because you have applied an external potential difference to it. This will be the EFI. Will be somewhere. This is EF, right? On the N side, the EF was closer to the right? It was closer to the conduction band. This is the bending Shurush here. This is the bending. Right? So the valence band here will be the intrinsic Fermi level. This is under reverse biasing. This bending has increased. Because of the built-in potential without biasing, it was difficult for an electron from the N side to move to this side, to the lower potential. Electron moves usually to the higher potential, right? Electron moves to the higher potential and a positive charge moves toward the lower potential. So this side potential is, we saw that the potential on this side was lower because it is in the direction of the electric field. So now the potential for the electron has rather increased, right? To move to this side. The potential difference has, what should I say? The potential difference has increased. This was, if you remember, the product of this value, the term value E phi n. Phi n was the potential difference and this was the energy. Similarly, the EF of the term value E phi p. Now this difference will be vertical difference now. The Fermi levels are not at the same position on the energy axis. If this is VR, V, the reverse bicycle. This is EVR. This energy is E. The difference available is when there is no external voltage applied, the Fermi level is the same across the junction. Now the Fermi level on the N side is lower. The P side, the Fermi level is high. Right? So it is more difficult for an electron to move to the lower potential because here the potential is lower. On this side the potential is low. On that side the potential is high. So for an electron, it's rather more difficult for the electron to move to the side. Right? Similarly, a whole energy increases down the the whole energy increases on the downward axis. So for a hole, it is difficult to move downward. For an electron, it's difficult to move upward. For a hole, it's difficult to move downward because a whole energy increases toward the bottom. Electron takes out key given the situation. Doesn't work. Valency of the conduction band. The more electron does it. Energy absorption.
Yes, sir.
Right? However, when a hole gains energy, it moves downward. Right?
Yes.
So this is what the situation is. Now, VBI was equal to, right? VBI was equal to phi n plus phi p, the Belgian potential.
Yes.
The marvelous sign was right. See, they are both positive.
Yes, sir.
Right? You have a negative, positive.
Yes, sir.
And similarly, the V total.
Yes, sir. Yes, sir.
They will be added together.
Yes, sir.
Potential difference is now added because the fields are not in the same direction.
Yes, sir. Reading so.
So therefore, the potentials will be added. The fields are added and the potential will be added.
Yes.
So it will be VI plus VR. Right? Now the width of the depletion region line. W is equal to V replace only the VBI by VBI plus R. Right? So it will be 2ES. Instead of VBI alone, VBI plus R. Divided by E and NA plus ND divided by NA and ND whole to the power 1/2. So the width increases the width of the space charge region will
Increase.
increase if you apply a reverse bias. The electric field, right? Electric field percentage, right? We know that the electric field will be in this direction in the space charge region, and we know from the previous situation, maximum field terrain, right? If you remember, the maximum field was at the center, x is equal to 0, 1.
Yes.
You remember that?
Yes, sir.
The graph as a field. So the value of the field, the magnitude of the field is greater at the center and is with 0 at both the. When the space charge region finishes, the electric field gets 0. Saida?
Yes, sir.
So the maximum was at x is equal to 0. So E maximum, two relationships from the previous situation. E maximum is equal to minus E and G xn divided by ES. And similarly, the same, you can get the same from the other side. Similarly, if you want to write it in the form of the XP, the whole, the P side depletion region, and in the form of the whole doping, Na. So it will be minus N E ES and XP. Right? Now we can put the value of xn and xp and use v is equal to vbi plus vr. Okay.
Yes, sir.
Value of xn are xp and using v is equal to vdi plus vr, we get E maximum is equal to minus 2E VBI plus VR divided by ES, and A and D double shift. And A and D and A plus and D into the power of 1. You put the value of xn or xp, and you get what? The maximum feed. What's popular?
Yes, sir.
Never on the issue. I'm not talking about then the questions they have. It is important too.
XT and XP.